In this problem, we also have rotation about the vertical axis, where our object is stuck to the wall because of that rotation. Here, however, we do have friction in the y direction, and that friction is going to be static friction because there is no sliding up and down. And for that reason, f of y is going to be static. And f of normal will be dynamic. And this I've written here where we have our a normal in terms of r and theta dot. We are to find the minimum rotation of the cylinder where this particle will still stay on the wall. So let's solve for that. Here we have a smaller zoomed in portion of that particle and just the forces. So this is a free body diagram. There's nothing external. For f of n, as I said before, this is dynamic, so it does not equal 0. And there is the normal force, and we have m, and this is positive, r times theta dot squared. For f of y, that is equal to 0. It's going to be static. There is mu static minus mg equals 0. Now let's plug this normal equation into our f of y, and you get mu of s times mr theta dot squared minus mg. Solving for theta dot with canceling out r's m, you get that g over mu s r and take the square root of that. All we have to do left is plug in the values that we know. And that is the square root of 9.81 over 0.4 times 0.5. And our final value ends up being that minimum rotation is 7.004 radians per second. And if you remember from previous values of omega, this is a pretty high acceleration from what we've seen before. Usually they can be less than 1, but here it's pretty large to keep that particle on the wall. So this has to be rotating very, very fast.